So now what if we needed to have the alcohol on the secondary carbon? We can't use acid and water because that gave us rearrangement. We're going to have to use some other chemistry, and that chemistry is called oxymercuration, demercuration. It avoids this formation of the carbocation, so therefore it avoids rearrangement. Now these reactions are still positive, but they're not true cations. So let's see how this works. The general reaction is this, plus mercury acetate in the presence of water will give us which then can be further treated with sodium borohydride to give us our alcohol. Now that's the generic reaction. Now that's a generic reaction. So let's see how it works in application. Let's see the mechanism first of all. So in the 5, 4, 3, 2, 1. So in the oxymercuration reaction, the reagent, mercury 2 acetate, dissociates slightly and a little bit in equilibrium to form this mercury cation. That mercury cation gets attacked by the alkene, by the pi bond of the alkene, to form what's called the mercronium ion, and this follows Markovnikov's rule. So when the alcohol attacks the mercronium ion, it'll attack to give you the Markovnikov product. Let's take a look. Let's imagine then we have our original alkene. And we have our first step, which will be mercury acetate. And H2O. Second step will be sodium borohydride. So what this is saying is that first we mix these things with this, magic happens, reaction takes place, and then we hit it with the borohydride. That's what it's telling me to do. Okay, so now we have to recognize that the mercury acetate is in equilibrium with its cation and anion. So HgOAc positive plus OAc negative. This bad boy gets attacked by the pi bond, and that's going to give us the mercronium ion, which looks something like this. Which now will be attacked by the water. To attack there, open up this ring here. Now notice what hasn't happened. We have not seen a carbocation. We saw a positive mercury, however, but no open distinct carbocation. There we go. Now notice that alcohol is protonated, so let's deprotonate this thing. And there you go. There's the deprotonated alcohol. Oop, got an H over here, sorry. All right, so now we have our alcohol, but now we got to get rid of the mercury, and that's where the borohydride comes in. So everything up to here was step 1. Now we're on step 2. So put a little square there. This is where step 2 comes in. Let's get rid of the square. Let's just put sodium borohydride right here. Sodium borohydride will replace the mercury with a hydrogen. That's what it does. The mechanism is kind of beyond the scope of this lecture or this course. So just remember that the borohydride will replace the mercury with a hydrogen. Just remember that for now. So we avoided the carbocation. So we avoided the rearrangement. So we got the product that we wanted. And that's how you would have to accomplish it. By using a different set of reagents that'll give you a different set of chemistry that'll give you different results. And that's how you do it. So let's discuss the stereochemistry of the water or the nucleophile attacking the mercuronium ion. When you have a mercuronium ion, the nucleophile must approach from the side opposite. Just like in an SN2 type reaction, the nucleophile must approach from the opposite side. And what does that do? Well, that tells me that the water that's approaching and the mercury will be what's referred to as anti. The water, the alcohol, will be anti to the mercury. They're on opposite sides. Because to work, the nucleophile has to come in from the side opposite of the mercury, similar to what you would see in an SN2 reaction, but not quite exactly the same as SN2. Okay, so just keep that in mind. So let's see an example, another example of an oxymercuration reaction. So let's see another example of the oxymercuration demercuration, just to make sure we're all on the same page here. 1-methylcyclohexene, or methylcyclohexene. All right, so what's the product of this reaction using the following reagents? So remember, the mercury acetate is in equilibrium with the mercury ion, mercury cation. So now the mercury cation is going to be attacked by the double bond. Now remember, let's imagine, if you will, the mercury came in from the bottom. Something like that. That means now that the nucleophile must attack from the top. Has to come in from the side opposite. Just like that. Has to come in from the opposite side. And that will give us this protonated alcohol. And that mercury compound. And this will be positive. So now, of course, more water will come in to deprotonate the protonated alcohol. And now, finally, we add the sodium borohydride. And that will replace the mercury with a proton. And that will give us our desired alcohol. Just like that. So that's how that mechanism would work. 5, 4, 3, 2, 1. Now, just in case you're wondering, can you substitute the water for an alcohol? I mean, alcohol looks just like water anyway, right? Except for it has some kind of alkyl group on it. So let's just see that. In fact, yes, you can totally do that. Mechanism is the same. No difference except for water. You put in, say, I don't know, methanol. And you'll get let's draw that up, and then down you'll get the methyl group. So yes, indeed, you can use alcohol for the same ends. The mechanism is exactly the same, except for where water attacks, now the alcohol is going to attack, and that's the only difference in these two mechanisms. So try this mechanism on your own. You'll see it's exactly the same as if water were the nucleophile.